Hello everyone, my name is Christian DeLucia and today's video is on basic statistical computations. And really what I mean by that is the kinds of computations that you would do by hand to get a sense of how the math works. Okay, so in stats, very few classes, in the social sciences, very few classes rival statistics for producing high levels of student anxiety. Um, a lot of basic stats classes, however, do not require advanced math. So I think the anxiety has less to do with math efficacy and more to do with a lack of stat efficacy in terms of being able to work through the basic computations or being able to figure out what the formulas are asking you to do. And so in today's video, we're going to take a look at some of these basic computations and try and demystify the formulas a little bit. So let's get to it. Okay, so first we're going to start with our sample data file. This data file is from a stats text Cohen, Weston, Aiken, and in the stats text, there are 15 observations on the data file. Here, I simplified it to 5 observations on each of 2 variables, X or vocab, Y or digit symbol. Okay, so we see we've got our column headings there. And then in the body of the table, we've got, 5 scores on a vocab subtest, 5 scores on a digit symbol subtest. And we're going to assume these are some neuropsychological measure that kids have been assessed on. Because we've got 5 observations in the table for each of the variables, our sample size, or n, equals 5. Okay, so the first formula I'm going to show you is, I would refer to that as sigma x sub I. And in this case, we're gonna sum over the various x values. We do a lot of this in basic stat computations. We do lots of summing over the various values of variables. Okay, so our equation there is written with the Greek letter sigma. Okay, the sigma has an index associated with it. At the bottom, we see I equals 1. At the top, we see n. And so that just tells the reader or the user that we're going to sum over the x values. We're going to start when x has an index value of 1, and then we're going to continue until we get to the last observation. N is standing in for the last observation or sample size, and in this case, our index variable ranges from 1 to 5. So in table 2, the variable on the left is the index variable ranging from 1 to 5. The variable in the center of the table is the x sub I, and then on the right-hand side, we have the actual x values. So in our top row after the header row, we see the index variable has a value of 1. So we see x sub 1 in the middle column, and then we see the actual x value on the right-hand side of 5, right? So for the first couple of rows there, we would say x sub 1 is 5, x sub 2 is 8, okay? The table note shows that I ranges from 1 to 5, where n equals 5. And then underneath, I just show that the sum of those 5 different x values will give us a sum of 39, which happens to be the answer to this question. And then I just make a note that the Greek letter sigma is a ubiquitous sign in stats text. So you'll see it all over a stats text. Next, I want to talk about summing over squared x values. In statistics, in basic computations, we do lots of raising numbers to powers, particularly squares. So I would read this equation, sigma x sub I squared. And that's, again, we're going to square our different x values, and then we're going to sum over those squared values. So in table 3, we've got the index variable, we've got x sub I, we've got the original vocab score, and then on the far right, we've got x squared. Okay, so in the top row, below the header row, we see that our x value is 5, our x squared value is 5 times 5, or 25. In the next row down, our x value is 8. 8 squared is 8 times itself, which gives us 64. And then you see down below, I give the sum of the 5 squared x values gets us to a sum of 319, which is the solution in this case. Okay, now on this slide, we're going to sum over squared deviations of x from the mean of x. Yes, that is a tongue twister, a little bit confusing. And this is a quantity that we see in lots of different stat formulas, and we call it the sum of squares of x if it's an x variable we're talking about. So here we've got the sigma symbol. In parentheses, we've got x sub I minus the mean of x, and then we've got the exponent 2 that is tied to the right hand parenthesis there. So that's telling us we're going to do the subtraction of the mean from each x value. We're going to square that difference, and then we're going to sum over the squared differences. So in table 4, the column on the left has the individual x values. The column in the center of the table has x minus the mean of x. We call that the deviation score. The note on the table tells us that the mean of x in this case is 7.8. So our deviation score in the top row of the table is 5 minus 7.8, which gives us a value of negative 2.8. And then on the right, in the right-hand column, we're going to square that value. So we're going to take negative 2.8, multiply it by itself, and we're going to end up with a square of 7.84. In table 4, in the bottom row of the table, I add the sum of each of the columns. And so on the far right-hand side there, we can see that the sum of our squared deviation scores is 14.8 in this case, which is the solution to our problem. So, so now I want to take a second and really talk about the process that we've been using. So on these first few slides, I showed you some basic equations. I walked you through a couple of intermediary steps, and we got to the answer, but I really stopped to talk about the process. And so I want to do that now. I've got an equation here that looks a little bit more formidable. This is one way we could write the equation for the Pearson product moment correlation coefficient. And so as these equations get a little bit more complex, we're going to want a fail-safe method to make sure that we can step through a series of intermediary steps and get to the correct answer. And typically what we rely on is the order of operations. Historically, when the order of operations has been taught in the early grades in school, we're often taught of the acronym PEMDAS, where the P stands for parentheses, E stands for exponents, M for multiplication, D for division, A for addition, S for subtraction. So in table 5, I give PEMDAS and I tie the various entities to a priority structure. Okay, so at priority level 1, which is our top priority, we've got parentheses and other grouping symbols. At priority level 2, we've got exponents or raising numbers to powers. And on the prior slides, we squared some values, and so we're already working with exponents. At priority level 3, we're going to have both multiplication and division. And at priority level 4, we're going to have both addition and subtraction. Okay, I make a note there that addition tied to the sigma symbol, the summation symbol, takes precedence over other addition subtraction operations. And then I also make a note that when we're working with multiplication and division, we work from left to right. And the same is true with addition and subtraction. We're going to work from left to right. Okay. On the next couple slides, I want to make a couple of additional points. Here I want to talk about fractions written using the horizontal fraction bar. So here's on the left-hand side, we see another way we could write the equation for the Pearson product moment correlation coefficient. So I've written it as a fraction using a horizontal fraction bar. Horizontal fraction bars are also grouping symbols. What that means is every time you see a fraction written like the one we see on the left-hand side of the slide here, I want you to imagine a larger set of parentheses or a set of brackets that captures all of the contents in the numerator. And then I want you to picture another larger set of parentheses or brackets that captures all of the contents in the denominator, okay? So to make that explicit, I rewrote the fraction on the right-hand side of the slide, adding brackets to both the numerator and the denominator. So in other words, when we're simplifying a fraction written in this manner, we're going to simplify the numerator first, then we're going to simplify the denominator, and then we're going to carry out the division, okay? And obviously, as we're simplifying the numerator and the denominator, we're going to use PEMDAS to help us execute our order of operations. So I want to make a couple points about square root symbols. We see a lot of equations written with the square root symbol. On this slide, I have two examples. On the left-hand side, I've got the equation for the variance of x. And on the right-hand side, I've got the equation for the standard deviation of x. And if you look closely at these two formulas, you'll see that they are identical with one exception. The formula on the right for the standard deviation of x has the square root symbol or the radical over the entire fraction, okay? And so when we've got a square root symbol written over an entire fraction, what we're going to want to do is we're going to want to simplify the contents in the numerator. Then we're going to want to simplify the contents in the denominator, and then we're going to carry out the division. And then in our last step, we're going to take the square root of that quotient. And that there are a couple different ways of solving a problem like that, but that will get you to the correct answer, okay? The other thing I want to mention about the square root symbol is that picture all of the contents under the radical as being enclosed within a set of parentheses. So another way we could say that is we could think about the square root symbol as a grouping symbol as well, okay? And so here I've got what I label our first official problem one. Now that we've looked at a couple of examples of solving these kinds of equations, and we took a moment to talk through the order of operations and a couple of additional characteristics, now we're in a position to put that knowledge into practice. Okay, so the way I would read this is I would say we've got the square root of sigma x squared multiplied by sigma y squared. Okay, we're thinking of the square root symbol as a grouping symbol. And so we're going to want to simplify what's under the radical first. So in table 6.1, I give a number of steps there. So in step 1.1, we're going to take care of our exponents. So we're going to square our x values. In step 1.2, we're going to sum over those squared x values. In step 2.1, we're going to square our y values. In square 2.2, we're going to sum over our squared y values. In step 3, we're going to multiply the sum of squared x values by the sum of squared y values. And then finally, in step 4, we're going to take the square root of the product, and that will get us to our answer. So here in table 6.2, I show you some relevant quantities. The column on the left has the x squared values. The column on the right has the y squared values. In the bottom row of the table, I've got the sum of squared x and y values. So sum of squared x values gives us 319. The sum of the squared y values gives us 1250. And so then I put the product of those two numbers, 319 by 1250, under the radical. And our answer in this case is going to be 631.47 or 0.47. Okay, our second problem, I would read that as sigma xy. When we see two variables written side by side like that, it implies multiplication. So if we think about our order of operations, we've got multiplication and summation using the sigma. And so our first step is going to be to multiply each x by each y value. And then our second step is going to be to sum over those products, right? So in table 7.2, I have the relevant quantities, we've got our X values, we've got our Y values, and then we have our X, Y products. So in the top row under the heading row, we've got 5 by 12 gives us 60, 8 by 15 gives us 120. And then in the bottom row of the table, I've got the column sum. So our sum of X, Y products is 630 in this case, which is the solution to problem 2. For problem 3, I would read that equation sigma x squared multiplied by y squared. Okay, so again, we've got powers or exponents, we've got multiplication, and then we've got summation with the sigma symbol. So in table 8.1, I lay out the steps. Step 1, we're going to square our x values. Step 2, we're going to square our y values. Step 3, we're going to multiply the squared x values by the squared y values. And then in step 4, we're going to sum over the products generated in step 3. Okay, in table 8.2, I show you the relevant quantities. The column on the left has the squared x values. The column in the center has the squared y values. And then the column on the far right has the product of those squares. And obviously these numbers can certainly, because we're raising numbers to exponents or squaring numbers, these numbers could get large. So again, the sum over the product of the x squared, y squared value is going to give us a sum of 89,948, which is the solution to problem 3. Okay, problem 4 is a little bit more challenging. We've got a fraction written using the horizontal fraction bar. So let's imagine all of our contents in the numerator enclosed within a larger set of brackets, all of our contents in the denominator enclosed within a larger set of brackets. And then we're going to simplify the numerator first, then we're going to simplify the denominator, and then we're going to do the division to get the quotient, which is going to be answer in this case. So step 1.1, simplify numerator. Step 1.2, we're going to compute the deviation score for x by subtracting the mean of x from each x score. Okay, so that's the quantity that's in the left parentheses in the numerator. Okay, in step 1.3, we're going to compute the deviation score for y by taking each y value and subtracting away the mean of y. That's the number that is in, or the equation that's in the right set of parentheses in the numerator. In step 1.4, we're going to compute the products of the XY deviation scores. In step 1.5, we're going to sum over the products of the deviation scores. By the time we hit step 1.5 and complete it, we have fully simplified the numerator in this case. Okay, so now we're going to shift to the denominator. Step 2.1 is to simplify the denominator. Step 2.2 is to compute the deviation score for x. Well, we already generated that in step 1.2, so we could just look at those values. In step 2.3, we're going to square each of those deviation scores for x. In step 2.4, we're going to sum over those squared deviation scores, and that's going to give us the sum of squares of x. And then in step 3, we're going to perform the division, and that's going to get us to our solution. Okay, so here in table 9.2, I've got relevant quantities. And so in our column on the far left, we've got x minus the mean of x. In our, as we move to the right, our second column is going to give us y minus the mean of y. And then our third column from the right is going to give us the product of those deviation scores. So those first 3 columns are relevant to what we've got in the numerator of the equation we're looking at. In the fourth column from the left, or the column on the far right, we've got x minus the mean of x squared, okay? And so that column is related to the denominator. And so our fraction is going to simplify to 21.6 divided by 14.8, and our solution is going to be 1.459 in this case. Okay. Want to make a couple of concluding comments first, and I think this is something that students get really confused about, there are a lot of different ways we could write equations for the same quantity. And so on this slide, I've got two different ways of writing an equation for the Pearson product moment correlation. Okay. And the equation on the left has n minus 1 multiplied by the standard deviation of x multiplied by the standard deviation of y in the denominator. And so under, at the bottom of the slide, I put the equation just to refresh your memory. I put the equation for the standard deviation of x, and you could use the same formula to get the standard deviation y. You would just substitute in the y values for the x values. Okay. And I did cite an entry from one stats text. And so here's the reference for that stat text. And I hope you enjoyed the slide set. And I hope after you work through the problems in the slide set, you'll feel a little bit more comfortable with these equations and these basic stat computations. Thanks for watching. Take care.